Have you ever been writing Python and thought, I love this, but I just wish it were faster? What if you could get the raw, metal-to-the-pedal speed of a language like C, but without leaving the cozy confines of Python? Well, that's exactly what we're digging into today. We're going to see how a modern systems language, Zig, is acting as the secret glue to make this happen, using a real-world tokenizer for LLMs called tokenizers as our guide.
All right, so here's our roadmap. First, we'll talk about a classic Python problem. Then we'll introduce our cast of characters, Python, C, and of course, Zig. After that, we'll see exactly how Zig connects everything, look at the nitty-gritty of how to build that connection, and finally explore what this all means for the future.
So, let's kick things off with a challenge that I'm sure every Python developer has bumped into at some point. It's that constant battle between a language being easy to use and being incredibly fast.
Yeah, I call this the Python paradox. On one side, you have this amazing language that lets you build practically anything in no time, thanks to its massive ecosystem. But on the other side, the moment you need to do some serious, heavy-duty computation, you hit a speed bump. Its interpreted nature can really become a bottleneck.
And there's no better example of this today than in the world of AI. Think about tokenization for LLMs. You are constantly breaking down huge volumes of text into tiny little pieces. It's repetitive, it's CPU intensive, and it has to be fast. This is exactly the kind of job where a project like tokenizerz comes into play, because Python's ease of use just can't keep up with the raw need for speed.
So, how do we solve this? How do we get the best of both worlds? Well, we need to assemble a team. So let's meet the key players in our story.
First, we've got Python. It's our friendly, versatile hero. It's the go-to language for basically all AI and machine learning development, but, it's not exactly a speed demon. Next up is C. C is the seasoned veteran. It's the bedrock of performance. It's fast, it's efficient, and it's lurking underneath almost everything, from your operating system to a lot of Python's own high-performance libraries. And that brings us to our star player, Zig. Zig is a modern systems language built for performance and safety. But its real superpower, the reason we're all here today, is its absolutely seamless ability to talk to C. It is the perfect universal translator for connecting these two worlds. So, how does Zig actually do it? How can these totally different languages just talk to each other? The secret sauce, the magic ingredient, is something called the C ABI. Right, the C application binary interface. Just think of it as the universal language of computing. It's a set of rules that defines how compiled code calls functions and passes data around. And since C has been around forever, pretty much every other language, including Python and especially Zig, knows how to speak this language. It's the common ground. And this is where Zig's elegance really shines. In the tokenizer.zig source code, you see this one little keyword, export. That's it. By adding that to a function, the developer is just telling the Zig compiler, hey, make this function available to the outside world, and make sure it speaks C ABI. It's that simple. But it's not just a one-way street. Z can also just use C code directly. This @CImport function is literally pulling in a powerful, battle-tested C library for regular expressions and making it usable right inside Zig. This is a huge deal. It means you can leverage decades of amazing C libraries without rewriting a single thing. So the whole flow looks like this. Your Python code makes a simple function call. Python's built-in C-types library then acts like a translator, converting that call into the C ABI format. The high-performance Zig library, which is already compiled to understand that format, does the heavy lifting at blazing speed. And finally, it just hands the result right back to Python.
Okay, that sounds great in theory, but how do we actually package up our Zig code so that Python can even find it? This is where Zig's modern build system is an absolute treat.
It turns out to be surprisingly easy. This one line in the Zig build script tells the compiler to create what's called a shared library. Now, depending on your OS, that's a .so, .dlib, or .dll file, all formats that Python knows how to handle right out of the box. But here's the really clever part. You can hook this whole process directly into your Python setup.py file. What that means is, when someone just types pip install tokenizerz, this little piece of code runs automatically, tells Zig to build the library, and puts it right where it needs to be. For the end user, it's completely seamless. It just works.
So, the bridge is built. The Zig code is compiled into a library, and it's sitting right where our Python code can see it.
Now for the payoff. Let's see how Python actually walks across that bridge.
And this is the magic moment, right here. With this single line of Python, we're using the built-in C-types library to load our compiled Zig code directly into memory. As soon as that line executes, boom, all of those super fast Zig functions are now available to our Python program. All right, there's just one last little step. We have to tell Python what the Zig function looks like, what kind of arguments it expects, and what kind of data it sends back. You can think of it like signing a contract between the two languages. Once you do that, you can call the lightning-fast Zig function just like any other Python method. It's completely transparent.
So, when you put it all together, what's the big takeaway here? What does this hybrid approach really unlock for us?
The bottom line is this. You get the best of both worlds. You get to keep writing code with Python's beautiful high-level API and its incredible ecosystem, but you can drop down to get the performance of C with the added safety and modern tooling of Zig for the parts of your code that are hitting a wall. And Zig acts as the perfect, simple glue to hold it all together.
This really just blows the doors open to so many possibilities. We saw how it can supercharge LLM tokenization, but just imagine. High-performance data analysis, real-time image processing, complex scientific simulations. Really, anywhere you've ever felt that performance pinch in Python, Zig could be the answer. The future of high-performance Python is looking incredibly bright, and it just might be a hybrid one.